Boolean operators and conjunctions. Comparison operators are operators that are used to compare two values. Each comparison operator will result in a Boolean answer. Our first symbol is less than. We want to talk about its opposite. Its opposite is not greater than. Its opposite is greater than or equal to. The reason being, if we have x less than 3, x less than 3 does not accept 3, so its opposite should accept it. That's why its opposite is greater than or equal to. Next we have greater than, its opposite is less than equal. We have less than or equal, its opposite is greater than. We have greater than or equal, its opposite is less than. Next we have equal equal, which tests for equality. You might be wondering why we do not use a single equals to test for equality. The reason we do not use a single equals is a single equals is the operator that's used for assignment, so we have to have a new operator. So the operator they chose to use is equal equal for testing for equality. Its opposite is exclamation equal or not equal. Not equal is true when the item on the left is different from the item on the right. Not equal's opposite, of course, is equal. Here's some quick examples. So I'm going to grab the pen and we're going to run through these. 5 less than 6. That is a true statement. 7 greater than or equal to 7. That is a true statement. 5 equals 3. No. That is a false statement. 18 is greater than 9. That is true. 5 is less than 5. That is incorrect. 4 equals 4. 4 is the value of 4, so yes, true. 19 is greater than 20. No, it's not. False. If that were less than, it would be true. 1 not equal to 5. That is true, they are different. 5 is not equal to 5. That is incorrect. 5 is less than or equal to 1. That is false. 8 is greater than 9. That is false. 3 is greater than or equal to 4. That is false. Comparison with objects. The comparison operators do not work as expected with objects, but all objects have built-in equals methods to test for equality. The format for using the equals method is object1 dot equals object2. We'll see some examples of that on the next slide. We will go into how the comparison operators work with objects in later chapters. So just know that if you're comparing two strings, you should not be using equal, equal, or not equal. Equals. We have A as apple, B as bear, and C as apple. Does A equal B? In other words, does the text of A, apple, match the text of B, bear? No. That'll give us a false. A dot equals C. That'll give us a true, because the text of A is apple, the text of C is apple. Conjunction operators are operators that combine two Boolean values and produce a Boolean result. The first one we're going to go over is AND. The AND conjunction produces a true value when both of its operands are true and false otherwise. The symbol for AND is ampersand, ampersand. The truth table for AND is if the left is false and the right is false, we get false. If the left is true and if the left is false and the right is true, we get false. If the left is true and the right is false, we get false. The only time we get true with an AND is if the left is true and the right operand is true, then the result is true. Or. The or conjunction produces a true value when at least one of its operands are true and false otherwise. The symbol for or is vertical bar, vertical bar. You may be wondering, how do I make a vertical bar? It's the key under the backspace. It looks like a broken vertical bar, but it will produce, on the font that we use, a solid vertical bar. The truth table for or. False, false will make false. False, true, this is a copy and paste error, will make true. True, false will make true. True and true will make true. So as long as there's a single true, either on the left or the right, our answer is going to be true. Short circuit. When a conjunction operator gets processed, the right operand is checked if it could affect the result of the conjunction. Another way of saying this, when the answer is known after processing the left side of conjunction, the right side of the conjunction is not checked. And short circuit when the left side is false. If we need both to be true, they both can't be true if the left side is false. So why waste the time checking the right? Or statements short circuit when the left side is true. You need at least one true to make the entire statement true. So if the first side's true, you do not have to bother with the second side. Let's look at an example of this. X is 9. Is x less than 4? No. This is going to give us false. So since we're doing an or, the other side could still be true, and that could make us happy. So we process the other side. Notice it's y++. That means use the current value of y, and then change y to be 1 larger. Is 9 greater than 5? Yes. So we get a true. As long as one side is true, the answer is true. So our output, I didn't make a little box for it over here, but let's say output. The first thing we print is the value of b, which is true. Then we print the value of x, which is 8, and then the value of y, which is 10. Let's move on to the next example. X less than 14. Is x less than 14? Yes, we get true. We do not process the right side. Because we do not process the right side, this y++ never happens. So when we do our output, we get true for the Boolean, and the value of x is 8, just like our last example, but the value of y is 9, because since we didn't have to do the right side, we didn't, and y never got changed because y++ never happened. Not. The not operator is a unary operator that will invert a Boolean value. So 3 greater than 7. 3 is not greater than 7, so we get false. But the opposite, or let me write it out, not false is true. Not 2 less than 4. 2 less than 4 is true. The opposite of true is false. And real quick, this would be not 6 equals 6. The opposite, 6 equals 6 is true. The opposite of that would be false. But let's say we had not 6 equal 6. 6 equals 6 is true. The opposite of that is false. The opposite of false is true. This would result in true. Another way to look at this, anytime you have an exclamation in front of an exclamation, they cancel in pairs. So every 2 exclamations will cancel each other. So exclamation, exclamation, they cancel. If we had 3 exclamations, 2 of them would cancel and we'd be left with one exclamation. All right, moving on. De Morgan's law. It is not always easy to read a Boolean expression that contains knots. De Morgan's law is a set of rules for converting an expression containing knots into an expression that does not contain any knots. The steps for applying De Morgan's law. Distribute the knots. When you distribute a knot, anything it affects, you should apply it to. Change the effected comparison operators into their opposites. Change the effected conjunctions, ands change to ors change to ands. Technically it's wrong. There's no such thing as not and. But for De Morgan's law, we just put the not there to remind us to flip the sign. You'll see in the next example. So here we have not x less than 3. So that was the only part the not was affecting. So right here is what changed. X greater than or equal to 3, the rest was unchanged. In our next example, the not is in front of the parentheses. That means it's going to be moved in when we distribute. So it goes in front of this first piece, it goes in front of the and it goes in front of the last piece. So when we apply all of those individual pieces, x less than 3 becomes x greater than or equal to 3. Even though technically we're not supposed to do not and, we're not leaving it that way. It's just a reminder that we need to flip the and. So the and becomes an or. And the opposite of not equal is equal. And this one's done. Here, we made one that's a little bit longer. Well, it's about the same length. So we distribute the not. So then we get not. Remember, these will cancel. That's how I end up with z equal 7. Not or is and. Not, the not is not affecting this x++. It's affecting the Boolean value. See, right here. Less than equal. So that's going to flip that to a greater than equal. The x++ is not affected because that's not a Boolean operation. All right. Creating random doubles. Format for creating a random double. It's math.random, which gives a number between 0 and 1. Notice it does not include 1. So 0 to 1, not including 1. That means 0.99999 times a value plus lowest number. Value is the number of whole numbers we could possibly get. Lowest number is the lowest number to generate. So if we did math.random times 10, there's 9 different whole numbers we could get because it doesn't include, value is the number of whole numbers. So the whole numbers we could get are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you count those up, that's 10 different numbers. But this will produce anything from 0 all the way to 9.99999, but not 10. If we do math.random times 5 plus 3, the lowest number we start with is 3, and we can generate that. And we can go all the way to 8, but not include it. Because remember, this is how many different whole numbers we could get. If you count those out, let's see, where do I get my hand here? 3, 4, 5, 6, 7. We can get to 7.99999, but we can't get to 8. All right, new shirt, new slide. Creating random int values. Format for creating a random int value. It's the same as creating a random double, except now you notice the whole thing is in parentheses, and then we cast that result to an int. We'll be truncating it or throwing away the decimal places. Value is the number of whole numbers you'll get. Lowest number is the lowest number that will be generated. When we do math.random times 10 and cast it to an int, that would make 0 through 9.999. But since we're throwing away decimals, it'll make 0 through 9. And since 0 is one of the numbers, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's your normal 9. And then 0 is also counted. So there's 10 different numbers it's generating. For the next one, we treat math.random times 5 plus 3 as an int. So the lowest possible number it can generate is 3. And there should be 5 numbers. If you count them out, let me get my hand up above the camera. 3, 4, 5, 6, 7. There are 5 different numbers it could possibly generate. All right, We're done.